Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on the 26th of June, 2025 T, 9 hours, 1 minute, and 19 seconds, .000Z. This paper, published just 2 days ago, presents a novel architecture that, surprisingly, did not improve the trade-off between performance and computational cost. The paper is titled, Learning to Skip the Middle Layers of Transformers, and we'll dig into why the authors think this promising idea didn't quite pan out. The authors designed a system to dynamically skip redundant middle layers in a transformer, hoping to make them more efficient for simpler inputs. Also, the authors shared their implementation on GitHub, and it's quite comprehensive. You'll find the full training codebase, which is based on Llama 3 and NanoGPT. They also provide instructions for training your own models, and even link to their pre-trained checkpoints on Hugging Face, so you can really dig in. And over on Hugging Face, you'll find their baseline models, from 115 million to 190 million parameters, all available for download with full model cards and usage info. Alright, so this figure really visualizes the core idea. We see a simple 4-layer model processing 3 different input tokens. The key innovation is the addition of these gate modules in the early layers. These gates act like learned switches. For each token, they compute a value. And if that value is 0, the model dynamically skips a whole chunk of the middle processing blocks. For example, for token 1, the gate at layer 1 is 0, so it bypasses blocks 1 and 2, saving computation. This is the mechanism they hoped would boost efficiency. Okay, so a key challenge is teaching the model when to actually use those gates to skip layers. This table details the different mathematical techniques the researchers explored to control what they call the sparsity of the gate values. Sparsity is just a measure of how often the gates are 0, which is what triggers the skipping mechanism. The loss column shows different penalty formulas they tested during training. The goal was to find a formula that encourages the model to close gates for simpler inputs, without hurting its overall performance. The adaptive technique proved most effective at this. Moving to the results, these plots show how that adaptive control actually played out. We're looking at performance versus computational cost. The vertical axis is cross-entropy, a score for model accuracy where lower is better. The horizontal axis on the left is inference flops, which stands for floating point operations, a measure of computational cost. Here too, lower is better. The blue dots are standard models, while the green points represent the new gated architecture. And this really tells the core story. The new architecture did not improve this trade-off between cost and performance. To give a bit more context on how they ran these experiments, this table lays out the default hyperparameters. These are the specific settings used to build and train the models, like the number of layers, which was 12, and the vocabulary size. The architecture itself is based on Llama 3, a very standard foundation. They also detail the optimizer settings. An optimizer is the engine that drives the learning process. And here they used a common one called AtomW. This all shows their setup was quite standard, making the comparison to the baseline models fair. So to wrap things up, despite this really principled design, which was based on solid insights about redundancy in a transformer's middle layers, the approach just didn't deliver the expected efficiency gains. The key takeaway is that this new architecture failed to improve that crucial trade-off between performance, measured by cross-entropy, and computational cost, measured in floating point operations. The authors do suggest, however, that this idea might still bear fruit at much larger model scales. It's a valuable reminder that even intuitive ideas need rigorous testing. That's all for this week's AI Research Roundup. Thanks for tuning in.